Good morning and welcome everyone to week 2 of our series giving an overview of the Australian Flexible Pavement Design System. So yeah, the presenter for today is the same as last week. Yes, it's me again, Geoffrey Jameson, and it's a pleasure to join you again. So today I think we'll take about an hour to get through the slides and presentation. And just a reminder to click on the Q&A button, type in the slide number related to your question as we go through the, and your question, and submit it as we go through the presentation. At the end of the session, we'll go through those questions. So as we discussed last week, the presentation, this whole presentation series is largely based around part 2 of the Austroads Guide to Pavement Technology, which is the pavement structural design method. Now, in relation to today's talk, there are other relevant parts that would be worthwhile considering and having a look at. And that's part 4A, the granular base and subbase, describing granular base and subbase materials. Part 4I, which is earthworks materials, so that's the subgrade materials. And part 4J, which is really the source rocks from which crushed rocks and natural gravels are produced. So have a look at those supplementary parts as well. So today we're talking about subgrades and granular materials and how we characterise them in pavement structural design. So I'll go through first looking at subgrade materials that we talked about last week in the introduction, how we determine the granular, the modulus, the design modulus we use, and unbound granular materials, again, how we determine the design modulus. And then we'll finish with some information about how we predict the performance of the pavement based on the subgrade and granular material characteristics. So in terms of subgrade, it is, of course, one of the most important elements that affects the pavement design. The thicknesses vary markedly with the amount of support provided to the pavement layers by the subgrade. So, and that support depends on the soil type, the density in situ, and the moisture content, both at construction and in service. And there's some of the challenges we have in coming up with the subgrade support value to use in the thickness design. So in terms of the Austroads system of design, the California bearing ratio is still widely used. It's been in use for about 80 years throughout the world, and it's still widely used in Australia for subgrade support to estimate the support. As I'll mention, we can also measure the modulus and come up with the elastic characteristics. But at the moment in Australia, we largely use the CBR test. And some of the factors that need to be considered when a designer is looking at estimating the subgrade support for the structural design, one of the key things is the subgrade variability along a project. These in situ materials, of course, vary markedly along the length of the road. And also another factor in that respect is what happens during the earthworks construction. Are materials moved, say, from cutting to full locations? So the sequence of earthworks construction is also important to know, or have an understanding of how materials might be reworked on site. Moisture content and density, as we'll see, play a major influence in terms of the subgrade modulus and subgrade CBR. The moisture content in service, again, a major factor. And that's also related to the provision of drainage, either both the subsurface drainage that might be provided to drain the pavement layers, and also the surface drainage and the pavement cross-section. So in terms of testing for the subgrade CBR, the sampling that's done along a project is very important, and this describes the sort of limited testing that might be commonly done. The subgrade might be sampled at intervals of 100 to 500 metres along a project. Try to look for combinations to address variations in soil type, topography and drainage conditions. But you can see with a natural material, even those sorts of intervals really have trouble picking up the variation in natural materials along a project. So we are limited by the amount of sampling and testing we can do for this variable material. So commonly for a new pavement construction, we would take those samples back and do laboratory CBR testing. And that is commonly a disturbed sample. You've taken the sample from along the alignment and you've done the laboratory CBR testing either in a soaked condition or an unsoked condition. There's also an ability to do in situ CBR testing. This is seldom done, but more commonly in situ, the dynamic cone penetrometer is used to estimate the in situ CBR. So this is an old photograph I have around in my collection of a CBR test being undertaken at the Country Roads Board. This would have been many years ago now. Looks like it was before the time the CRB could afford stainless steel moulds by the look of this, the rusting in this equipment here. Nevertheless, the test itself is you apply a load to a plunger and you estimate or measure the load for a given penetration of that plunger into your prepared specimen. So the loads are measured at 2 depths of penetration, and those loads are expressed as a percentage of the load for the same penetration required for a crushed rock. And the index test that was originally used was a Californian crushed rock. And so it's a percentage of those loads for a Californian crushed rock that is recorded as the value. So for our crushed rocks in Australia, for example, in Victoria, we often get much greater loads than required for the Californian crushed rock. And so we have CBRs can be well in excess of 100%. So in turning back now to the subgrade again, when we're doing the subgrade CBR testing, it is important to do the testing at the appropriate field densities and moisture contents in situ. And this shows here what is a CBR contour, where you're looking at the effect of both density and moulding moisture content on the CBR value. And for example, if you thought the in situ CBR, the in situ densities were about 100% of standard Proctor compaction, you could go along here and see the significant variation in the CBR for minor changes in the moisture content. And you can see here how significant small changes in moisture content are to the CBR result. And this is for a clay sand. So as I mentioned, density is an important factor that needs to be considered. And when we do the lab tests and interpret those CBR contours, there needs to be a selection of what density to assess the CBR at. And that could be an in situ density that you measure, but more commonly, it's related to the minimum value that you might specify for construction. And that's commonly in terms of the percentage standard Proctor maximum dry density. That would be a common way, say 100% of standard Proctor maximum dry density. In terms of the test conditions, the moisture conditions to use during the CBR testing, in the Austroads guide, there's some typical moisture conditions that are being used. And you can see here the compaction moisture content that you use to prepare the specimen, and whether it's soaked or unsoaked, the testing can vary depending on the rainfall and also the drainage that you anticipate along the project. Now, commonly 4-day soaked CBR results are used and compacted at OMC. That's the most common method of preparing and testing the specimens. But in some states, like New South Wales, they use a lot of 10-day soaked CBRs. And each state has some slightly different rules for coming up with those test conditions. And this is shows you an extract from the Queensland Pavement Design Manual, where they could use an unsoaked value for rainfall up to about 800 millimetres. Now, whereas above that, they might use for very bad, very poor high rainfall areas, or for floodways, causeways, etc. You might use a 10-day soaked CBR, and then more generally a 4-day soaked CBR. But these sort of rules, for example, that rule about 800 millimetres wouldn't apply in Melbourne here. Melbourne's rainfall is less than 600 millimetres, less than 800 millimetres. But Vic Roads, for example, if they were designing a pavement in Melbourne, would you use a 4-day soaked CBR? So these rules about moisture content conditions and soaked and unsoaked vary from state to state, and there are differences in practice throughout Australia. But that just gives you one example of the guidance that Queensland provide, for example, about the test conditions. I mentioned earlier about in situ testing to estimate subgrade CBR, and the most common method is the dynamic cone penetrometer, where you apply a load to a rod and you measure how much it penetrates the subgrade. And as you see in that little chart there, you can, for given number of blows, you can measure how much it's penetrated. And from that, you can estimate from the penetration values and the variation of those number of blows to give a certain penetration, you can estimate the subgrade CBR. And this is the process we currently use for estimating the subgrade CBR from the penetration in terms of millimetres of penetration per blow. So there's a process there that can be used. This test is more commonly used in pavement rehabilitation, where you're testing an existing pavement rather than in the design of new pavements where the pavement doesn't already exist, or the subgrade doesn't already exist to test. So this is a test more commonly used in pavement rehabilitation. Another means of estimating the subgrade CBR, instead of doing some laboratory soaked CBRs or some in situ CBR testing, is use some presumptive values. And this is commonly, it plays a very important role in coming up with the design CBR. We've provided in the guide some presumptive values that are based on experience, basically, of what designers have used according to the material type, the material classification, whether the subgrade is a heavy clay, highly plastic clay, a silt, a sand, a sandy clay, for example. And these are really based a lot on experience and a lot of past laboratory testing. Now, for example, in Melbourne here, it would be in the west of Melbourne, where we have basaltic clay subgrades in the western part of Melbourne, it would be common to use a design CBR of 2 or 3. Whereas in this side of the city, in terms of in the eastern suburbs and and down to peninsula. You might have sandy clays or silty clays, and you might be using a commonly used value of 4 or 5 for a design CBR. Now in Perth, there's a lot of sand in Perth, a subgrade. It's predominantly sandy subgrades, and they use a value of design CBR of 12 routinely in Perth. So they wouldn't bother to estimate the CBR, to measure the CBR in Perth. They would already have sufficient results around from a number of years to just use a presumptive value and a shown value of 12 in that case. So it's quite an amount of use of presumptive CBR values as well as lab-soaked CBR values. Now, in terms of the mechanistic empirical design, of course, CBR is not terribly useful to us. What we need is a modulus value, so to use in our linear elastic model. And in our linear elastic model, subgrade materials are considered to be elastic. And as I'll talk about later, there's no consideration of the stress dependency of those of subgrade moduli. In terms of how we estimate the modulus values, we have a rule here. We multiply the design CBR by 10 to estimate the vertical modulus, and the horizontal modulus is assumed to be half the vertical modulus. So this is called cross-anisotropic characteristics. The modulus is different in the horizontal direction than the vertical direction. And we have some information also about presumptive CBR, Poisson's ratio values to use in our modelling work. Now this relationship, this 10 times CBR relationship is shown here, this solid line here. This is the Austroads relationship here. And for, a CBR of 10, of course, the modulus, the vertical modulus is 100. But you can see there are various other relationships used in other countries and by other road authorities. For example, this pinkish one here was the one developed by TRL in the UK. And you can see that the values you would get in terms of vertical modulus is very different from the 10 times CBR value that we use in Australia. Because of the limitations of this formula, some road agencies limit the use of that formula to a maximum of about 100 MPa. So they don't continue to use it, say, up to a CBR 15 and assume its modulus 150. Now, for example, Vic roads for heavily trafficked roads would limit the design CBR to a maximum of 100, regardless of whether or not they actually measured the CBR of their subgrade to be 15 or thereabouts. And as I mentioned earlier, there's no allowance in that 10 times CBR formula for the stress dependency of modulus values. And in 2012, we did some finite element modelling of how the modulus of the subgrade would change with the stress levels. And you can see here, this pinkish line here, for example, is a sandy clay with a CBR of 6. If you have very low stresses, the modulus that can develop is a lot more than 6 times 10, 60. It can be quite a lot higher, whereas at high shear stresses, it can be lower than 60 MPa. We make no allowance for that stress dependency in our Austroads procedure. We have one rule, 10 times CBR. And this just explains that a little further. I've given an example here that we did in 2009 where we're showing here, the pink line here is for an unbound granular pavement with a sprayed seal surface. And this is for a subgrade that's got an in situ CBR of 7, so maybe a design CBR of 70. we would use in design. There's our 70, and that 70 value might be applicable for thin layers of granular material on that subgrade where the stresses are quite high, but it would underestimate how the subgrade support when the granular thickness is a lot greater. Similarly, if we have a significant thickness of full depth asphalt, which has even lower stresses than the granular pavement, you can see that how much greater the modulus of the subgrade would be if we took account of the stress dependency of the subgrade in coming up with the modulus value. And that just shows you some of the limitations of the current process of using one value of 10 times CBR for all pavement configurations. And you can see that maybe it should be varying with pavement configuration because that alters the stress levels. And we looked at it again a few years later, and this gives you some further information about also we don't consider in our mechanistic model variation in modulus with depth below the top of the subgrade. We just assume one value for the whole semi-infinite layer, and there's no allowance for the fact that the stress is reduced with depth, and therefore the modulus should increase. So I'm just running through some of the limitations of what we have in terms of the design system. And because of those differences in the way you would characterize the subgrade modulus between running, say, a finite element method, we allow for the stress dependency, and the Austroads linear elastic model using 10 times CBR, you can see in this slide here the differences you can get in the critical strains that you use to predict pavement performance. And the values that you would use if you allow for the stress dependency can be a lot lower than what we currently use. So we've talked a lot about CBR and how you come up with a design modulus from CBR and some of the limitations of that. For a number of years, at least 30 years in Australia, we've had an ability to do repeat load triaxial testing of subgrade materials. And shown on the slide here is some results I undertook in sort of 30 years ago in the about 1990. We measured the characteristics of a sandy clay here in Melbourne. And so those tests have been around, but they're not routinely used. They're limited to research. And we don't yet have an Austroads procedure for testing subgrade materials in repeat load triaxial testing. And one of the challenges is for us is some of the materials like the clay subgrades can have optimum moisture contents have equilibrium moisture contents above the optimum moisture content. And so there are some challenges there about how you compact specimens for repeat load testing from material that is above OMC. So we have yet to standardise procedures for doing repeat load testing and getting the modulus values in that way, but it has been used in research. So if you like some further information about those issues that I've raised, there are two reports here that are referenced in the set of slides that you might want to turn to and look at some of the work we've done exploring some of those issues. So just a reminder, if you've got any questions, please click on the Q&A button. Please give me the slide number that the question relates to and send it in, and we'll address those questions at the end. So turning now to unbound and granular materials, again, I'll run through some of the issues and the processes we currently use and some of the issues related to the current processes. So when we talk about unbound granular materials, commonly, they could be natural gravels, shown in the left-hand photograph on this slide here, where a natural gravel is being broken down by a grid roller in situ, or it could be a crushed rock, like shown on this shot on the right-hand screen, which was construction on the Hume Freeway from Melbourne and Wodonga in the 1980s, where a large paver would pave the crushed rock full width and then would be compacted. So in terms of crushed rocks, they are manufactured at a plant. They could be split into different sizes and then recombined, or it could be what's called a crusher run, where the crusher is just set to give you a desired grading and you don't sort it into different sizes and recombine it. Granular materials weren't always like this in terms of being crushed and nicely graded materials that we use today and placed mechanically. There were times when granular materials were hand placed and larger pieces of aggregate we use. So it always hasn't been like what we use today. In terms of the distress modes for granular materials, we're concerned about the rutting and shoving of granular materials due to insufficient shear strength and or due to densification. If they haven't been compacted adequately, they might rut by densifying under the traffic loading. The other way you could get rutting is if the granular materials degrade in situ. It might be a chemical degradation with time due to a poor quality aggregate, and you get a breakdown of material. So there are some of the distress modes that might you would see in terms of granular materials. And in terms of rutting and shoving, it is the rotating shear stresses of materials close to the loads, the base course materials, that are important as far as their rutting characteristics. And shown on this slide here is some accelerated loading we did on a crushed hornfells in Melbourne, and showing some rutting here that we got within 24 hours of starting the experiment. So some of the tests that we do use for granular materials in terms of strength, modulus and deformation, again, we use the California bearing ratio test. It's still used in Australia. And there is some use of the repeat load triaxial test, but not widely, but it is used in Australia, particularly where you're talking about recycled materials and comparing those to new pavement and new granular materials that can be used in specifications for granular materials that include recycled materials. Now, of course, the CBR is still used, is commonly used for granular materials, and this shows the Unbound granular thickness design chart, the empirical one that we discussed last week. And for example, on that chart there, it gives the cover requirements for different strengths of materials, and included in those materials could be subbase materials, materials under the base course, granular subbase materials. So it would give, the CBR test is quite useful to know, to classify the material in terms of strength and therefore know how much the cover thickness required over that material to inhibit deformation of that subbase material under the base course. And again, we saw that previously, our CBR test. These are some of the typical values that might be specified for granular materials in terms of a crushed rock base. Might be specified by a greater than 80% would be a value that would be used. Upper subbase, 30 to 40, and then lower subbase, say 15 to 30. Now, in the mechanistic design, as we discussed for the subgrade, we need modulus rather than CBR. So, because we need a modulus for the trial pavement configuration when we're trying to predict the critical strains in the pavement. And those strains could be the asphalt strains to predict asphalt fatigue, or the tensile strains at the base of cemented materials to predict cemented materials fatigue, or it could be the vertical strain on the top of the subgrade, which we use to predict surface deformation. So we need a granular modulus to calculate those strains, those critical strains in our mechanistic process. And again, in our mechanistic design, we use a linear elastic modulus value. And again, the modulus, we're considering the granular materials elastic. And cross-anisotropic again, as we discussed for subgrade materials, and we have presumptive Poisson ratio values to use. Now, how do we come up with the design modulus for granular materials? So in the Austroads guide, it's designed as a resilient modulus obtained from the laboratory repeat load triaxial test at the appropriate density, moisture, and stress conditions. So that's our definition. And it is a resilient modulus. So you calculate that from the applied axial stress and also the measured resilient axial strain on unloading. So it's a resilient modulus value that we measure in that test, and it is used in defining the design modulus. Now, some of the factors that affect the granular material modulus, the critical ones are really stress level. So the modulus increases with mean normal stress, completely different from that of subgrade materials, which go the other way, which reduce rather than increase, and also decrease with shear stress. Moisture content, again, as you increase the moisture content, the modulus reduces, and also density. The higher the density, the higher the modulus. So the modulus you measure, of course, depends on the shape of the material. It also varies with the grading or the particle size distribution of the material, whether it's a well-graded material or gap-graded or finely graded or coarsely graded material. So there's some of the factors that affect it. In the guide, we give an example of how the modulus might vary with the density, and you can see a few % change in the density can make a significant difference to the modulus that you would use in design. And also how the modulus reduces with moisture at the higher the moisture content. We provide some advice there about how the significance of moisture content in coming up with your design modulus. This is an example of the stress dependency of, I think this is probably a crushed rock here, showing on the vertical axis is the resilient modulus that measured at different mean normal stresses and also different values of the octahedral shear stress. So you can see that the modulus increases with mean normal stress and also reduces with the octahedral shear stress. But we're limited in our ability to allow for stress dependency in our linear elastic model that we use in Austroads. Remember that we use one modulus value for the entire layer, horizontally and vertically. So in terms of allowing for the modulus stress dependency, we're limited in what we can do in a linear elastic model. And nonlinear finite element method is a much improved method of estimating the modulus at a certain applied stress level. We have developed some sort of workarounds for that limitation in the Austroads linear elastic model. And for example, to allow for the change in modulus with depth, we sublayer the total granular thickness into 5 equi-thick sublayers. And we need to determine and then assign a modulus value for each of those sublayers to try and allow for the stress dependency of modulus values. And the modulus that we assign to each of the sublayers depends on the modulus of the top layer, and I'll explain the next couple of slides how that is determined, and also the modulus of the underlying layers, which could be the subgrade, and also the thickness of the granular material that you're subdividing. So in terms of the determining the top granular sublayer modulus, we can measure that with the repeat load test, but it's commonly not done, but it can be done. You can measure it and calculate a value at an appropriate stress level for your pavement configuration. And, you know, that's some results there. For example, you could pick the modulus value appropriate for the stress level that you predict, say, in the top granular sublayer, and use that as your top modulus value. But more commonly, designers use presumptive values. And in the guide, we provide these presumptive values that have been used for many years, for over 30 years, much the same advice is applied. And for example, for a high quality crushed rock, you might use 500 MPa as the top layer when you're talking about the modulus under a thin bituminous surfacing, like a sprayed seal surface that we talked about last week. And that would be a common value used in Victoria, for example. In other states, particularly New South Wales and Queensland, they more commonly use what's called a normal standard crushed rock, which gives them a presumptive value of 350 MPa. So a much lower modulus than what's assumed commonly used in Victoria for the quality of materials in Victoria. And then you have a presumptive value for a base quality material, and also some presumptive values for sub-base layers. So these presumptive values are widely used. We seldom measure the modulus and then determine the top modulus from those measurements. Commonly, the presumptive values are used. And the other thing that, of course, as I mentioned earlier, is, I think I did, is the stress level affects the modulus, and that stress level that's applied to the granular materials varies with the modulus and the thickness of the overlying bound materials. So, for example, we've got thick asphalt layers above a granular layer. The thicker the asphalt is, the lower the stress is applied to the granular material, and therefore the lower the modulus values. So how do we allow for that in the design? Again, we have some presumptive modulus values to use under different thicknesses of bound materials, and this could be the thickness of overlying asphalt, and different modulus values of that overlying asphalt or cemented material. And you can see here how the modulus values reduce with depth because the stress is varying with depth. So this is another workaround for use in our linear elastic model to overcome the deficiencies of not allowing for the stress dependency of individual layers in terms of the granular modulus. And so the granular modulus in the design system is also limited by the support provided by the underlying materials. And it could be, for example, where a granular material is placed on a subgrade, it'd be the subgrade modulus value that would limit the top granular modulus. And you can see here that, for example, to reach a top modulus value of 350, a lesser granular thickness is required for CVR 10 than it is for a CBR3. So we allow for the influence of the subgrade modulus and the thickness of the granular material in estimating what granular modulus can actually be achieved. So again, it's a workaround, a simple rule trying to allow for something that's more complex in a simple system. And when we look at the finite element modelling about the effect we see there, it does confirm the fact that we should be limiting the support to the granular that's generated, limiting the granular modulus depending on the support provided by the subgrade. You can see here that we have modelled different subgrade modulus values, and we've then plotted what the finite element method generates in terms of the subbase modulus at the bottom of that layer. And you can see the higher the calculated modulus in the subgrade in this finite element modelling, the higher the modulus of the subbase. So that provided us some reassurance that we're on the right track in terms of limiting the modulus assigned to the granular layers depending on the support provided by the underlying subgrade and also the granular thickness. So this slide here just shows another limitation, or much along the same lines as previously, to the fact that when we do a linear elastic characterisation, we assume a constant modulus at different distances away from the centre of loading, as shown by this solid line here. This is, for example, 350, a presumptive value that might be used for a normal quality granular material. And in the linear elastic model, we would use a value of 350 regardless of how far we are away from the centre of loading. Shown in these other points on the graph is the results of finite element modelling, where we allow for the stress dependency of the modulus value. And for example, this curve here is the top of the base course, and you can see much values in excess of 350 occur quite close to the surface, whereas it doesn't take long before the modulus value at further away from the load, the further you get away from the load, so this area here where it's above 350 is essentially almost underneath the wheel of that we model. So you can get values around maybe 500 or so rather than 350 in the finite element, but it drops off markedly with distance here. And we don't allow for that in our simple, there's no way of allowing for that in a linear elastic model. To allow for that horizontal, there's no workarounds that we've been able to come up with for that limitation. And again, because of that, if you compare the results of finite element modelling in terms of critical strains versus our current Austroads procedures, you can see quite different strains that you get out if you haven't allowed for some of the stress dependencies in the most accurate way that you could do it. So about 10 years ago now, Austroads asked, commissioned ARRB to develop a non-linear elastic model. And we did that, and it's capable also of doing, operating in a linear elastic mode. From that work, Austroads concluded it was not suitable for routine design at this stage. But there is a linear, non-linear elastic model around that could be used for modelling. And again, if you'd like some further information on that, that project that we did to look at non-linear elastic modelling, that's the report to reference. Just a reminder again, please send in your questions if you have any. So turning to the final element of our presentation this morning, I'll just talk about, we've talked so far about response to load and how modulus values and how we characterize those in a response to load model, a linear elastic model or a finite element model. We haven't talked about predicting performance of the road. And so now I'll just give you a few slides here about predicting the deformation of granular materials and subgrade, because that's the stress mode that we design for these materials. It's not fatigue, they're not bound materials, but we look at their deformation characteristics. So what we design for is the surface deformation, or the surface rutting, if you like. And we use what's called the subgrade elastic strain criteria. Now, it's a misnomer that we've used here because people get confused about, we're calling it a subgrade elastic strain criteria. And the immediate thought is often people think, well, we're predicting the subgrade permanent deformation from the subgrade elastic strain. Well, that's not the case. We're actually calculating the subgrade elastic strain, and from that, estimating the allowable loading in terms of surface deformation. So it includes deformation of the granular materials and deformation of the subgrade from an estimate of the subgrade strain. And later in this series, we'll discuss how that strain criteria was developed. But just keep in mind what we're talking about here is a strain in the pavement that relates to the deformation of the surface and the allowable loading in terms of the surface deformation. So we have a criteria like that that limits deformation, but also it's complemented by empirical information we have about what materials have worked well in the past for different traffic loadings and for base and sub-base. And some of the empirical tests that we use are, of course, the particle size distribution, the CBR test, and also plasticity tests. These are empirical tests that are used in conjunction with the subgrade strain criteria to select materials that have the right deformation, appropriate deformation characteristics for particular uses. And this is an example here of what VicRoads, for example, the empirical information they provide in their Unbound granular chart. So instead of the Austroads system just having a line for base course and saying this is the minimum quality of base course required, VicRoads tie the qualities of materials to their specifications and say, particularly as the traffic loading increases, there are minimum thicknesses here of different qualities required, regardless of what the chart says. So it's a combination. What we use in design is a combination of a mechanistically determined subgrade strain criteria, plus some empirical design rules based on experience with materials by different road agencies and tied to their specifications. Now, the deformation can also be estimated, as we talked about, from the repeat load triaxial test. And there's a test method around for that, the Austroads test method for measuring the deformation characteristics of granular materials. But what we've found is that the test, when we've done tests looking at how the test results measured in repeat load, the permanent strain results that we measure in the repeat load test, compared with the performance of materials, we haven't found that it correlates well and provides we haven't found it provides a good means of ranking the performance of different materials. And we've done that sort of testing using our accelerated loading facility here in Melbourne, and this shows, for example, ELF working with a triaxial configuration in our test laboratory in Dandenong. Commonly, we just use a single axle, but this was looking at the effects of different axle group loads when we were doing this testing. So it's from this sort of testing where we're trying to simulate long-term performance of pavements that we can get information to compare the laboratory tests against. So we've used that sort of information when we've made those, undertaken that research. So from that research that we've undertaken, we've developed, to replace the repeat load test, we're suggesting a large-scale wheel tracker test is better correlated with the deformation of base course. But it's commonly at the moment, there's only one in use in Australia, and we have it at ARRB, but it's used in research largely, has been used on a couple of projects for routine design, but it's not commonly used for routine design. So that measures the deformation under a rolling wheel, and we're applying rotating shear stresses with that test, as opposed to the repeat load triaxial test, which isn't the one that we use in Australia anyway, isn't rotating the shear stresses. So we've found that that provides a better means of ranking materials than the repeat load triaxial test. But one of the challenges we have in this whole area is our ability to predict in-service moisture contents. And you can see here the results that we've got from the wheel tracker tests in terms of the allowable number of cycles to a deformation of 10 millimeters versus the degree of saturation. So if we have an error of about 5% in degree of saturation, we can't predict it within about, you can result in a factor of 5 or 10 in terms of the number of load cycles to a agreed deformation level. So you can see it's highly sensitive, the performance, to your ability to predict the moisture content in situ. And this is one of the biggest challenges we currently have in improving our design processes. Just to reinforce that a bit further, when we talk about 0.5% in moisture content, that's equivalent to about a spoonful of water in a kilogram sample of granular material. So it is a real challenge to be able to predict and also measure moisture content to that sort of accuracy. And yet that sort of accuracy can still result in quite a deal of uncertainty in terms of its performance, whether a pavement would last 10 years, 20 years, 30 years, or 40 years, for example, could vary markedly on your ability to predict the moisture content. So my colleague Didier has done a lot of work in trying or researching methods and providing a framework for improving our ability to predict deformation. And so I refer you to his report in 2013, where he goes and assesses the ability to predict the deformation using finite element modelling with different models there to predict performance. So this is some of the research reports that are relevant to this topic that I recommend that you review and have a look at. So just a reminder to please send in your questions. So what I've gone through is I've gone through the elastic and characterization of both subgrade and unbound granular materials. And then I finished off with some slides showing how we predict the surface deformation, surface rutting due to deformation of granular materials and subgrade materials, and also some of the challenges there, both in terms of our ability to come up with appropriate elastic characterization of both subgrade and granular materials, the limitations of linear elastic modelling, and also the limitations of how our ability to predict the deformation of pavements. So now I'd like to hand it back to Arun to give us run through the questions, and I'll see if I can field some answers.
Thank you, Jeff, for such a great presentation. We'll move on to the questions now. We got a couple of questions from the attendees. The first question is from Anand, RMIT, on page number 74, slide number 74. There is a significant increase in degree of saturation during the test. And he's wondering whether the water comes from during the lab testing you presented.
Well, this is a result of doing wheel tracker tests and I think it goes up a bit further, that test there, of slabs prepared at different moisture contents. So we prepare them compact the specimens at different moisture contents, and then we test them with the wheel load, and the results shown there are the result of testing slabs prepared at different moisture contents.
Thanks for the clarification, Jeff. And Anand asking another question. Thanks for the presentation. It has been shown that the mechanical behavior for both subgrade and granular material is highly dependent on moisture. For subgrade soil, the moisture content affects the suction and thus changes the suction stress of the subgrade. For fine grain soil, suction level can be very significant. But for the granular material, the suction level is usually very low. And he is wondering what would be the key mechanism accounting for the influence of moisture on the mechanical behavior of granular material. It's a big long question, but I can repeat if you want.
We haven't done a lot of work in terms of pore pressures and the influence that you're talking about, but I think I've demonstrated through the series of slides here the significance of that. When we measure the characteristics, both the modulus values of subgrades and of granular materials, the variation with moisture content affects modulus values significantly, and also the deformation characteristics. So the challenges there is really developing procedures that can improve what we currently do, but also recognize the limitations of how well we can predict the moisture contents of materials. So to me, that is the biggest impediment we currently have, is our ability. This is our ability for using these procedures in design, I mean, not as researchers, but in terms of implementing the research findings, it's our ability to predict the moisture contents, for the design to be able to predict what the in-service moisture contents are going to be is the biggest challenge, because it needs to be very accurately predicted.
Thank you, Jeff. And the next question is, what is the typical range of equilibrium suction in unbound material layer and subgrade in Australia, based on your experience?
I haven't got that information. I think you could probably find some values in the literature, but I don't have that information with me.
No problem, Jeff. And the next question is on page number 70, or slide number 70, figure 8.2.
Right.
Why is there a huge increase between stage 1 and stage 2?
Yeah. Why is there an increase?
Yes.
You see on the top of the graph there, the different deviator stress levels that are applied in the different stages of the test. So the test, the Austroads test, consists of 3 stages. You start off with a deviator stress 350 kPa, then you increase at stage 2 to 450, and then you do a final stage up to 550 kPa. So that's why there's a jump. The modulus value increases between 1 and 2 because the stress level is increased. But you can see in this case, you're actually getting a modulus reduction happening with cycles of loading in stages 2 and 3, which indicates that something is happening that's not beneficial to the material, even in this repeat load test, that it's not actually increasing or being stable with time, but it's actually reducing in cycles of loading. But the permanent strain results that we get from that test weren't a good indicator of the performance of these 4 materials here. They didn't rank the materials like we got under accelerated loading. So the results in terms of the permanent strain values weren't useful for us in ranking these materials.
Thank you for answering the question, Jeff. Moving on to the next question on slide number 61. What were some of the arguments to deem is not suitable?
Some of the arguments related to the effect on design configurations. Now, I think it was recognised that the strains that you would predict with the nonlinear finite element model would be closer to the truth, if you like. It would be a closer representation of reality. But then the question became, if we use those same strains in the design, and as I showed you, some of the strains are significantly lower than what we currently use, and we didn't change our performance relationships, we would estimate much greater lives than what we currently do in our design model, and therefore it would imply that the thicknesses of pavements could be reduced. There was concern that we would need to recalibrate the performance relationships. If we changed the method of predicting the strains and provided more appropriate predictions of strains, we would have to, there was no evidence that we would we needed to change the pavement thicknesses. That was the upshot of it. If we did change those strains, we would change the performance relationships such that similar thicknesses apply as currently apply. So in terms of, unless there was some information available, and until such time that it was available, that it was agreed the changes were required to the thicknesses that designers calculated, well, then there wasn't much benefit in going to a more complex response to load model. So that was the upshot of it, was that there was no agreement by designers that the implied thickness changes from changing to this process were appropriate. So there wasn't any benefit there to them. They were saying, well, we would still, there's no information in this by providing a better response to load model that we really need to change our thicknesses, because that thickness in our mechanistic-empirical method is based on empirical information about field performance. So we might come up with an improved response to load model, but there wouldn't be a case that the thicknesses that we construct should change from that research. So they were struggling to appreciate why we would change to a more complex system of response to load modelling.
Thank you, Jeff. And the next question is, have the effect of confining stress for RLT been studied for permanent deformation, considering that the base material is so close to the surface?
I'm not sure what slide number that relates to.
I didn't specify any slide number. I think it's a general question for RLT.
See if I can find a slide that relates to that. So the question was, has the effect of confining stress been considered? Is that right? In the modulus characterisation?
The effect of confining stress, yeah. considering the base material is so close to the surface?
Well, in the repeat load test, in our repeat load test, we provide a constant confining stress. It's not cycled, and it is considered as far as you can see there, calculation of the mean normal stress includes confining stress as part of that calculation, and also it affects the octahedral shear stresses. So the model that we have includes the effect of confining stresses both through the mean normal stress and the octahedral shear stress.
Mm-hmm. Thanks, Jeff. And the next question is on slide number 43. Here. So what is the specified in situ moisture content and density recommended to achieve in situ conditions for the construction of unbound pavements?
What is the in situ moisture content?
Moisture content, yes, and density.
Well, that is up to the designer to select appropriate values that reflect the constructed densities and moisture contents. Now, in terms of density, what would guide the designer would be what values are the minimum values that are acceptable for construction. And those specifications for constructed densities vary between road agencies. For example, in Victoria, it might be 100% of modified Proctor maximum dry density, might be an appropriate density level to use. Whereas in other states, it might be some percentage, 100% say, or 102% of standard Proctor maximum dry density. So there are different standards of acceptable densities in different states. And what's the guiding thing is trying to estimate the in situ values. The moisture contents are more difficult to assess in terms of what moisture contents the results should be at. And the road agencies often specify a minimum degree of saturation or percentage of optimal moisture content at which they would seal the pavement ready for opening to traffic. And that might be 65% of OMC or 70% of OMC, somewhere between 60 or 70%. And that is not uncommonly used, that sort of moisture content, when results are being assessed from the repeat load triaxial test. But we know that moisture contents equilibrium values may be more like 50 to 60% of OMC. So it's an area, again, where there's no real guidance. It's left to the designer to come up with appropriate moisture content for the project, considering all those things like drainage characteristics, the rainfall in the area, the evaporation, et cetera, So it's a judgment made by the designer.
Thank you, Jeff. And the next question also on RLT. The sample height used in the triaxial test is almost similar to the thickness of the base material. So the triaxial stress state may not reflect the in situ stress condition. Could you please comment on that?
So some question about whether the test applies appropriate stresses, is it?
Yes, the stress state, yes.
I'm not aware of that concern. Maybe we could discuss that outside the webinar series, but I'm not aware of a concern. We do have, as you can see there, a load cell. I think that in terms of the deformation characteristics, the main concern we don't have so much concern about the Modulus characterization with this test. The concern relates to its use for permanent deformation, because we're applying an axial load, a vertical load. We're not applying a rotating shear stress in this test, and that's our concern about the use of this test.
Thanks, Jeff. And slide number 23. The question is, could you please go through the test contractor to establish the elastic modulus relationship?
Right. In this report that's written in 2012, we looked at the literature, and for each of those materials shown on the slide there, we tried to characterize their stress dependencies. So we looked at the available information that was published, and you'll see there's some presumptive stress dependencies given in that report for both granular materials and for different subgrade types. So if that may be of interest to researchers to look at that report and have a study what we came up with about presumptive values of stress dependencies for different materials. So that's where they've come from. We've looked at the literature and we've come up with some presumptive stress dependencies, and that forms the base. That was then used in our nonlinear elastic modelling to calculate how the modulus value changed with the stress level. So we did that for both the subgrade and also the granular materials. We looked at the literature and came up with a set of presumptive values. So that might be of use to researchers.
Thanks for the clarification, Jeff. And the next question is on slide number 21. Is there any analytical model to calculate the stress transfer from tire pressure at the road surface down to the subgrade?
Is there any, what, sorry?
Analytical model.
Well, this linear elastic model, you can calculate the stress levels in the pavement with this linear elastic model. But as I mentioned earlier, a more accurate means of estimating both stresses and strains is to use a non-linear finite element model that allows for the stress dependency both vertically and horizontally. And so that would provide a better means of estimating the stress levels of different parts of the pavement.
Thanks, Jeff. And the next question is on slide number 20. It's on the pavement drainage. How the type of drainage for a pavement structure is decided, on what basis, whether it depends on the designer's decision or environmental factors?
You'll see through a lot of this discussion that what we provide in this Austroads system is guidance to designers. We rely on engineering judgment of engineers in making assessments for individual projects. And I talked about that a bit earlier with moisture content we're talking about. And the same applies here in terms of you can come up with some guidance here about typical values that might be used, but it's up to the designer to look at an individual project and make some judgment from using his engineering judgment, his engineering expertise, to come up with a judgment of the drainage conditions on that site. So it's not quantified, it's left to engineering judgment, a lot of these elements in design. So we don't have an ability to predict the moisture contents and the effect, we don't have an ability to predict the effect of drainage. So it's left very much to the engineering judgment of the designers to come up with an appropriate value.
Thanks, Jeff. The final question is on slide number 18, 19 together.
Which one? 18?
The 18 and 19 on DCP.
Right.
Yeah. The DCP test estimates the subgrade CBR with the depth. What CBR value should be taken as the CBR of the subgrade in designing the pavement? Is it the CBR of first 300 millimeter thickness or first few billows?
Yeah, we're largely silent on that, providing guidance on that in the Austroads system. But I think the general consensus would be it would be the top 300 millimeters of the subgrade would be, because that's often the limiting value. When you look at the values, it is commonly lower at the surface of the subgrade. perhaps due to the fact that the moisture contents are higher there than they are at depth. So it is commonly, you would look at the variation with depth and make some judgment about, the designer would make some judgment about whether to use, whether there be any reason not to use, put it that way, the top 300 millimeters.
Thanks, Jeff. We answered all the questions, and I now hand over the session to you.
Right, thank you very much. Well, thank you all for attending this session we had today. I hope you found it of some use. Next week, week 3, we'll be looking at bound materials, asphalt and cement materials characterisation. So I hope you'll be able to join us then. So thanks again for joining us today, and look forward to next week and discussing that with you next week. Goodbye.